Hello, this is Mirbagheri. I'm going to present similarity matching of temporal event interval sequences written by me and my supervisor, Dr. Howard Hamilton. The outline of this presentation starts with introduction. We're going to talk about the motivation and the problem that we're going to solve. Then we have problem statements. We're going to have few definitions and the preliminaries basically that we are needed to have for this paper. And then the method that we propose to similarity match is going to be discussed. And then number 4 is experiments that we have conducted in this paper. And finally, we're going to conclude the presentation. Interval-based event sequences, or so-called E-sequences, are the sequences of events persist over intervals of time of varying length. They exist in many application domains such as medicine, sensor networks, and sign languages. The E-sequence datasets, though, have problems. They contain longitudinal data where instances are described by a series of event intervals, and they don't have features with a single value. So, and they are not organized appropriately for standard machine learning algorithms, so we cannot apply directly these algorithms to these datasets. Now we present some definitions and preliminaries. An event interval E is a triple LBF where L stands for event labels, B is the beginning time, and F is the finishing time. For example, A for 8 means we have event label A that starts at time 4 and ends at time 8. E sequences is a list of M event intervals that they place in ascending order based on their beginning time. For example, Swan, where we have A from 4 to 8, B from 6 to 12, and so on. Then E-sequence dataset is the set of n E-sequences where each E-sequences is associated with a unique identifier. Here is an example of E-sequence dataset with 4 E-sequences that may represent, for example, 4 patients and 6 event labels A, B, C, D, E, F in this dataset that may represent type of disease that patients suffer over a period of time. Let's take sequence 4 from previous example to explain more definitions presented in this paper. So each sequence is slice time. It basically is the unique time point that exists in every each sequence. So, for example, for sequence 4, we have this list starting from 4, as I said, so it's going to represent the unique time point that exists in sequence 4. And then we have coincidence function that's going to give us the event labels that occur at some point, some given point. For example, if we have 510, we plug it 510 to this function, we get CDE as the event labels that co-occur between 5 and 10. So then we have coincidence label sequences or L sequences, which is ordered list of coincidences excluding the gap. So we get the result of the coincidence from this slice time for all of them. So we're going to pair every slice time and then plug it to this coincidence, and then we get this list of coincidences. So what problem we are going to solve? So the problem that we are interested in is the similarity searching and matching of full-length E-sequences. The contribution that we are making in this paper is basically proposing and evaluating three novel approaches to this problem. And we intuitively view the similarity between two E-sequences is an S prime or any two sequences in terms of presence of event interval with the same event label, order of occurrences of these event intervals, duration of the event intervals, and because we are also considering the duration of the event intervals, so this event interval is going to make temporal relation that is classified based on the Allen temporal logic that we're going to follow. And so therefore, we are also going to consider temporal relations among these event intervals. The first method that we're going to propose is a matching using relative frequency. So this is the formula that we use. So in this formula we use duration of the event interval and duration of the E sequences. So the duration of event interval E, for example, in sequence 4 is 14 minus 4. So we used finishing time minus beginning time of each event interval to get duration of event interval. And then duration of the E sequence, for example, in S4 is the maximum finishing time, which is here in this example is 22, and then minus the minimum beginning time, which is 4 in this example, and we get 18. So we're going to use this formula to get the relative frequency of each event label in sequence, and then we're going to define another function f1 that's going to map an e sequence to a vector of the relative frequency. So if we apply this function to the data set, the e sequence data set that we showed you in the previous slides, then we get these vectors, relative frequency vectors of all sequences. For example, here we have S4, and then as you see here, we don't have any A here, so the relative frequency of A is 0, and then based on that formula, we get different numbers for each event labels. So because we have now magnitude of the relative frequency, we can use Euclidean distance to get the distance between each sequences. The second method that we are presenting is matching using position code. So the position code is a function that we define to represent the position of every event label in an E sequence based on the code. So this is the function that we are using the coincidence and L sequence to get the position of event labels in its E sequence. And then we define another function f2 that's going to map the E sequence S to a vector of the position codes of event label, similar to the previous method that we represent each E sequence in vector. This time we're going to represent each E sequence based on the position code that they have. And because the code, the magnitude of the code doesn't have any meaning here, we use cosine distance to get the distance between the position code vectors of E sequences S and S prime. So we call this method or this distance function EPC function. Third and last method for similarity matching that we are proposing is using multiple kernel learning. We define a function named EMKL to combine the result of the two other functions that we already defined, ERF and EPC, to get weighted linear combination of these two functions, and then find the distance between two E sequences S and S prime based on these functions. We are presenting the experiments that we have conducted in our work. So 8 real-world dataset was used in our work. So the statistics of this dataset are shown in this table. We evaluate our work based on performing first nearest neighbor classification, prediction for every E sequence in dataset, and then we get the accuracy. Also, we compare it with the three competitors' dynamic time warping based method, Artemis and IBSM. The result of our experiments are shown on this table. As you see here, EMKL, which is our method, outperforms the Artemis and dynamic time warping based methods on all datasets. And when we compare with the IBSM, it outperforms on 4 datasets, ties on 2, and loses on 2. In conclusion, we propose 3 distance functions to match the full length of event interval sequences. The ERF function measures the distances of each sequences based on the relative frequency of the event intervals. The EPC function matches each sequences based on the position codes of the event intervals. And lastly, the EMKL function combines the ERF and EPC function result to get the final output. And the result of experiments shows that the EMKL method is an effective approach to this problem and is a better choice compared to the state-of-the-art method.